The environmental lapse rate, or the average value anyway, is when the temperature decreases with altitude, roughly 6.5 degrees per kilometer, rise in elevation. All right, so that's kind of where I left off last time. All right, so that's and again that varies. This is just an average value. All right, so now let's say you had here. So let's say that you had air. So but before we get into this unstable air, I want to describe what stable air is. Right. So you imagine an air parcel, right? So an air parcel is is um, is descending. Let's say the air parcel descends, and of course, what happens then when the air parcel descends, it the pressure goes up because it's lower in the atmosphere. Um, and then the temperature begins to rise, right? So the temperature rises, but when the temperature rises, the density of the air molecules will decrease, and so when that happens, that parcel of air. Okay, so again, we're not talking about unstable. This is stable air. That parcel of air will want to rise again because it's gone down enough so that the temperature has increased, causing the density to decrease, and then when the density of the parcel decreases compared to the atmosphere, the surrounding atmosphere, and so that parcel wants to go back to where it started. All right, and the same thing goes for a parcel that starts out lower in the atmosphere, right? So let's say the parcel begins to rise, and so what happens when the parcel rises, the temperature goes down. But when the temperature goes down, the density of the parcel, the density of the air molecules inside of the parcel, that they go up. And so when the density of the air inside of the parcel goes up, that means that the density is greater than the density of the surrounding air. And so that parcel of air will begin to go back down again. Right? So the fact that both of those situations, the parcel that was descending and wants to go back up, it doesn't want to, but the change in temperature and therefore the change in density causes it to want to go back up. And the same thing for the one that was forced up. So it's forced upward. The temperature goes down, but the density of the parcel goes up, and that forces it back down to where it started. So both of those situations are stable air. So the parcel is considered stable. All right. Now, so now we can talk a little bit about unstable air. All right. It's really the parcel that's unstable. All right. So if rising air stays warmer than the surrounding air, it will continue to rise instead of return to its starting position. So like in both of those situations that I mentioned before, it the, you know the one where you had the air rising, the air rose and then it returned back, right? Because of the increase in density. But for unstable air, it just continues to rise. I mean, it eventually it doesn't rise anymore because it becomes the same density as the surrounding air. It's really what's called buoyancy that keeps that forces the air up or down. But anyhow, if the air doesn't want to return to where it started, especially rising air, if it doesn't return to where it started, then that's considered unstable air. All right. So as it says, eventually the air particle will expand and cool to match its surroundings. When the temperature matches the air particle stops rising, but it doesn't sink back to its starting position. Right. And so those unstable rising air tends to form these cumulus clouds. right? And in other words, that's that indicates what's going on with the weather. That's one way that people have used for a long time to see if to figure out what's going to happen with the weather. All right, stable air resists upward vertical motion and tends to form clouds that spread out. These are called cirrus clouds. All right, so cumulus clouds, unstable air, cirrus clouds, or stratus clouds. I should have. Cirrus or stratus clouds tend to form when you have stable air. All right, so it's being able to identify the cumulus clouds, the cirrus clouds, and the stratus clouds. All right, so that's and for that, sometimes it's just better to just look at pictures, which we don't have yet. I think they're coming up. All right, so anyhow, this is a kind of interesting situation where normally we think of the as you go up. The standard thing is as the elevation rises, the temperature goes down. But there can be this thing called the temperature inversion, right? So there's a really good example of this, and this is why Los Angeles has all this smog, and besides the fact that it has a bunch of people driving around in cars, one of the most populous cities on the planet. But what happens is, you have the Mojave Desert, and so you have hot air passing, from the mountains passing over Los Angeles, and then you have cooler air from the ocean, because Los Angeles is right on the Pacific Ocean. The cool air underneath, rising up from the ocean, but that hot air above does not allow the cool air to rise, and so you have this temperature inversion, and so all the cars putting out all the exhaust fumes and so forth, that creates this stuff called smog, and it just sits there. It'll just sit there for a very, very long time, until it rains or something like that, which really doesn't happen. I lived in Southern California, and it does, of course, it rains sometimes, but certainly not that often. All right, anyhow. All right, so let's see, what is this? Weather variables. What does the image below demonstrate? Okay, so this is the Golden Gate Bridge, of course. As of the time of this recording, I've never actually been over the Golden Gate Bridge. I've been underneath it many times, many times, because my ship. I was in the Navy, and so my ship used to sail underneath it, and we would dock, right at San Francisco, and but I've never actually driven over the Golden Gate Bridge. So someday I might do that. All right. Anyhow, and San Francisco, by the way, is an absolutely gorgeous city. If you have never been out there, it's really fantastic. Anyhow, so what you're seeing right here is fog, of course. So that would be condensation. That's all. That's all that one is. Condensation. All right. Let's see. So this is just classifying the different clouds. All right. So let's go back to what we were just mentioning. All right. We have cirrus clouds, which happen to be really, really high up. I'll go into the different, these different the alto and cirro and so forth. Then you have stratus clouds. And then there are cumulus clouds. Okay, so cumulus clouds, as we mentioned before, have this vertical development. That comes from unstable air rising, and not returning. Whereas cirrus clouds and stratus clouds, these other ones we'll describe in a little bit more detail in just a minute, or in a little bit. But anyhow, these two come from stable air, right? All right, so So these are basically the different ranges in how high these things can rise. Um, so there's also besides cirrus clouds, there's cirrostratus and cirrocumulus. The mid-level ones are you use the prefix alto, so altostratus and altocumulus, and then the lower ones. So it's they classify it in terms of this one's these are above 6 kilometers. These are between 2 and 6 kilometers. These are below below 2 kilometers. Um, so those are stratus, and then stratocumulus, and then nimbostratus, and then of course the ones that have this vertical, they begin to develop as that unstable air rises. Those are cumulus and cumulonimbus. Sometimes it's fun to say that stuff. All right. Clouds develop when the condensation rate exceeds the evaporation rate. Remember that graph that we looked at several videos ago. All right. So when rising air partial cools at the dry adiabatic lapse rate until it saturates, right? So it can only rise so far, and then what's going to happen? It cools down, right? And so you're gonna reach that dew point very quickly as the parcel rises, right? And so when that happens, then you're no longer talking about dry air. You're talking about air that's reached the saturation point just because it's risen up higher, and the temperature is lower. Remember, lower temperature, the parcel can hold less air, and so you reach the dew point sooner. All right, so then it follows what's called the moist adiabatic lapse rate, and remember that's a little bit less. That's around 6.5, something like that, degrees Celsius per kilometer rise, and that controls how thick the cloud will become. So you can have clouds as here, let's go back to this. When they talk about these clouds, these are where the bottom of the clouds are. The top of the clouds are dependent on this adiabatic the moist adiabatic lapse rate. All right, the height of the clouds and how thick they depend on the environmental lapse rate, the dry adiabatic, right? Is that that will and then the moist adiabatic lapse rate. The cloud will form once this leads to this, right? Once the dew point is reached and you're in the moist adiabatic lapse rate, and then the environmental lapse rate will tell you how high the thing will rise. All right, so these are the ones that are up really high. Those are called cirrus clouds. All right. They kind of they look very wispy. They're not the billowy type of clouds that you normally sometimes you associate with clouds, the big cotton looking things. Those are actually the cumulus. All right, what happens to the relative humidity of an air partial at the lifting condensation level? Okay, so let's see, what happens to the relative humidity of an air partial at the lifting condensation level? Let's see, so the relative humidity increases and the air partial stops rising. The relative humidity increases to 100%. That sounded really, and the air partial becomes saturated. That seems pretty true. Part C or answer C there. The relative humidity decreases and the cloud formation begin. No, that's not true at all. So C, I would